Welcome to today's Explainer. We're diving right into a seriously fascinating tension right at the heart of modern AI. If you build, use, or honestly even just study AI, you've probably hit this wall. Language models are, well, they're inherently chaotic. Today, we're going to unpack the architectural secrets that the very best engineering teams are using to literally tame that chaos. Let's get into it.
So how do you build reliable software out of unreliable parts? It's the core paradox of building production-grade AI right now. Think about traditional software engineering. If you write a function to calculate a user's shopping cart total, you expect it to be right, 100% of the time, right? But generative AI? It just doesn't work that way. So how on earth are companies building reliable, enterprise-ready systems using components that might literally give you a slightly different answer every single time you ask them?
And this brings us to the fundamental tension. We are taking literally the most predictable system on Earth, classical code, and fusing it with the least predictable system, stochastic large language models. Look, classical code guarantees that the same input run through the same code always gives you the exact same output. Always. Large language models, though, they don't execute, they sample. They're just picking tokens from a probability distribution. You can send the exact same input and get a totally different output. It's wild. To solve this engineering mystery, here's our roadmap for the Explainer today. We're covering 1. The predictability paradox, 2. Why code never surprises, 3. The math of AI chaos, 4. Building the deterministic cage, and 5. We'll wrap up with the flight control analogy.
All right, Section 1, the predictability paradox, code versus chaos. Here is the absolute crux of the thesis. We don't actually want to get rid of the unpredictability. I know that sounds crazy, but that chaos, that's exactly what makes the AI smart. If an LLM was perfectly deterministic, it would just be a giant rigid lookup table. It wouldn't brainstorm, it wouldn't parse messy text, and it definitely couldn't generalize across new concepts. So you don't try to eliminate the unpredictability. Instead, you build a strict, deterministic cage right around it. Code is the container, and the LLM is the intelligence trapped inside that container.
Moving on to Section 2, Why Code Never Surprises, the Foundations of Determinism.
If we rewind a bit and look at Turing machines and the von Neumann architecture, physical execution on a CPU is completely predictable, literally down to the instruction level. It's just fetch, decode, execute, write back. Given the exact same memory state, every physical CPU produces the exact same output. It's rock solid.
And over the decades, we've layered on all these beautiful classical guarantees. Pure functions, no side effects, f of x always equals y. Type systems, your compiler absolutely guarantees an integer won't magically become a string. Finite state machines physically cannot enter an undefined state. But here's the massive problem we're facing today. Every single one of those guarantees disappears, just poof, gone. The exact second you send a text string across an API boundary to an LLM, the compiler goes totally blind.
Which brings us to Section 3, the math of AI chaos, why LLMs are unpredictable.
LLMs generate the next word by sampling from a probability distribution. When you mess with settings like temperature, top P, and top K, the model is literally rolling mathematical dice to pick the next token. Now, you might be thinking, okay, I'll just set the temperature to 0. Boom, deterministic. Nope. Even at temperature 0, distributed GPU hardware creates total chaos. Floating point math across these GPUs is non-associative. That means microvariations in server loads or batch processing orders actually change the math at a microscopic level, and that cascades into spitting out completely different tokens.
To really prove this point, researchers ran this amazing experiment. They sent the exact same prompt to a model 10,000 times at temperature 0, and guess what? They got about 100 unique outputs. To get just one perfectly identical answer across all 10,000 runs, they had to painstakingly control every single piece of the infrastructure to stop that floating point variance. It's wild. The randomness, the stochasticity, is baked right into the metal these models are running on.
Let's get into the solutions. Section 4, Building the Deterministic Cage, the Production Playbook.
So how do we actually force control over this chaos? First, constrained decoding, and libraries like Pydantic. This physically restricts the LLM's token choices at generation time, forcing it to output valid JSON. It's basically bringing static typing to generative AI. Second, state machine guardrails. You define exact workflow states, like planning versus executing, and strictly restrict which tools the LLM can even touch in each state. Third, temporal or durable execution. This separates the deterministic replayable code from the totally non-deterministic retriable LLM activity. And finally, formal verification, using math and logic solvers to double-check the LLM's output against hard rules before actually executing anything.
What's really cool is that every single modern LLM safeguard is actually just a classical computer science concept wrapped around the prompt boundary. Type systems, finite state machines, event sourcing, formal grammars. We're just taking these old-school, rigid concepts and using them to contain the probabilistic engine. We aren't inventing new computer science here, we're just applying the classics as a heavy-duty safety wrapper.
And the impact of this is massive. By wrapping LLM activities in deterministic orchestration logic, like Temporal does, production systems are hitting a 99.99% completion rate. The workflow orchestration is purely deterministic and replayable. If your system crashes, the event history just rebuilds the exact state. Meanwhile, the LLM call itself is just treated as this messy, non-deterministic activity that you can retry. It handles timeouts and rate limits with exponential backoff without breaking a sweat.
This whole philosophy builds into an architecture known as blueprint first. The old way of doing things was basically asking the LLM to decide the entire workflow, giving it the keys to the kingdom. But that much autonomy almost always leads to failure, looping, and crazy hallucinations. The new way, the blueprint first approach, means you write the workflow in standard, boring, deterministic code. That code is the blueprint. Then you only call the LLM for very specific, tightly bounded subtasks. The code is driving, and the LLM is firmly buckled into the passenger seat. And the data absolutely backs this up. Keeping the LLM as a bounded subtask drastically outperforms fully autonomous agents. Recent benchmark tests on complex user tool rule scenarios showed a massive 10.1 percentage point improvement when using this blueprint-first framework. Turns out, if you just let code do what code is good at, the LLM becomes vastly more effective at its actual job.
Section 5, the flight control analogy, pulling it all together.
I absolutely love this framing because it just nails it. The LLM is the probabilistic brain. The code is the deterministic skeleton. Think about it. A brain on its own is just a chaotic bundle of firing synapses, right? It physically needs the rigid framework of a skeleton to actually interact with the world reliably.
A modern flight control system is the perfect analogy for this. Your classical code is the autopilot. It maintains altitude, follows hard mathematical rules, and physically cannot enter an undefined state. The LLM? That's your AI copilot. It's incredibly smart. It handles the messy radio calls, interprets fuzzy weather reports, makes route suggestions. But, and this is absolutely crucial, the formal verification layer of the autopilot will simply not allow the plane to fly upside down. No matter what the AI copilot suggests, the physical limits of the system deterministically block it. Any truly reliable production AI system stacks up exactly like this. You have your deterministic shell, the code, schemas, and state machines setting the rules. Inside that, you have the probabilistic core, the LLM inference handling the actual meaning and intent. And surrounding that core is the validation boundary. It acts as the ultimate gatekeeper, mathematically checking the LLM's work or flagging a human before any real action is taken. So the big takeaway here? Programming doesn't make LLMs predictable. It makes them usable. We aren't replacing software engineering with prompt engineering, not even close. We are using classical software engineering to contain, manage, and safely deploy this brand new probabilistic intelligence. The secret to production AI isn't finding a model that never hallucinates, it's building a system that catches and corrects those hallucinations long before they ever reach the user. So I'm going to leave you with this. Going forward, what parts of your systems need a probabilistic brain and what parts absolutely demand a deterministic skeleton? I highly encourage you to look at your own workflows through this lens of chaos versus control. Next time you're building an AI feature, don't ask the LLM to do everything. Seriously, ask yourself, what needs the flexible brain and what needs the rigid skeleton? Thanks so much for joining me on this explainer, and I can't wait to unpack another complex topic with you next time.